For our second lecture of the week, this is for Wednesday, October 24th, the subject is buoyancy. When we were talking about locomotion, I made the point a number of times that it's important for animals to maintain their position in the water column. There's certain features of water, meaning in the medium of water, as opposed to air, that make that easier. There's other aspects of moving through water that aren't so favorable, overcoming drag for the most part. So there's pluses and minuses of having a life as an aquatic organism as opposed to a terrestrial organism and moving through air versus moving through water. But nevertheless, they're very different environments that require different types of movement if you're going to survive and thrive. Well, in the ocean, aquatic organisms, it's important for them to maintain the position in the water column, and a lot of that has to do with buoyancy. So these are the subjects that we're going to talk about this week, are hydrostatic lift as opposed to hydrodynamic lift. If you swim through the water, your fins generate a certain amount of lift if you're a shark. They lift you up like the wings of an airplane. So, you can have jets that don't have that big of wings, but they move very quickly. They generate a lot of lift, and their wings are oriented. The front part is bigger, and they taper off to the thin part in the back. There's a lot of hydrodynamic lift that we've seen, but there's some places in the ocean, in particular the deep sea, where there's not that much energy to be a jet. You can't fuel swimming around very quickly and generating all this hydrodynamic lift. So there's your typical shark that weighs about 5% more than the water. So they're 5% heavier than water. That means they'll sink if they don't swim. But you could lift one up with your hand, just like you could hold somebody up in a swimming pool, because if a shark weighs 100 kilograms, it's only 5% of that weight that you're experiencing. You can lift that up 5 kilograms rather than 100 kilograms, just like you can hold up some really big person in the water with your one hand or even a finger. So we're going to talk about hydrostatic lift, which, as the name implies, refers to lift that's generated without having to move. Second thing is the liver. The liver is a hydrostatic organ of sharks and skates and rays. They don't have a swim bladder. They're not like bony fish. Their liver carries out a lot of different functions, detoxifying things, and it's related to digesting things. There's a whole bunch of different functions of the liver, but one of the functions that's important for the success of sharks and skates and rays, especially some groups, is their liver. And if you look in the liver, it's oil that's low density. It's lighter than water. If you think about an oil spill, the oil's on top of the water. Oil and vinegar, salad dressing, the oil is on top of the water. Oil is less dense than water. And it's oil that these sharks store in their liver to use as a mechanism of lift. Obviously, there's different types of lipids that carry out different functions. So if you look in the body of a shark or skate or ray, they've got a number of different types of lipids that do different things. But one of the main functions of lipids in relation to this topic that we're talking about is in providing lift, hydrostatic lift. As I mentioned, there's a number of different types of lipids. You've got triglycerides, diglycerol ethers, and you've got ethers, you've got wax esters, you've got phospholipids. There's a number of different types of lipids, again, that do a number of different things, have a number of different functions. If you look at the types of lipids that are common in the livers, then these sharks tend to have, if you're a shallow water shark, then they're not much different from other animals. There's a lot of triglyceride. If you look at deep water sharks, they've got some unusual lipids that you don't find in very many animals or plants, and they're low density. Low density lipids. And then we'll look at how those all relate to the density of the animals. So we're talking about hydrostatic lift. This is the lift that's generated not from swimming. It's lift that's just generated by the relationship between the density of matter that's in the body and the density of the water in which the shark finds itself, or the skate or the ray. So, in terms of dense matter, you've got things that are more dense than water, basically. If you're thinking about the different components that make up the body of something, you've got dense matter, which means that it's more dense than water. If you look at seawater around the world, the density of seawater is usually about 1.27 grams per cubic centimeter. That's a unit of density. You know, there's some water that's less dense, 1.025, 1.026. There's some water that's a little denser. As you go deeper, then the water tends to be more dense. But a typical value for density of seawater is about 1.027. You know what the density of pure water is, right? You learned that someplace, some class. The density of pure water is 1.000 grams per cubic centimeter. So what in the body of a shark or skate ray is more dense than water, seawater? Inorganics like salts, sodium, chloride, calcium, those things tend to be dense. 1.39 compared to 1.027. That's a very dense. Skeleton is dense. They've got a skeleton of cartilage, but it's still pretty dense. 1.3 as opposed to 1.02. That's more dense. Muscle is a dense tissue. Skin is pretty dense. Even organs tend to be more dense than seawater. It depends on the organs, but you know, they've got tissue that is more dense, connective tissue and muscle tissue, those kind of things that are more dense than seawater. What is light in a shark? Ovaries have oil in them. They tend to be less dense than water. Just a little less dense than pure fresh water, but this is seawater. So 0.99 as opposed to 1.027. That's low density. And then you've got lipids. A typical lipid, triglyceride, has a density of about 0.92. That's light in comparison to water. So the point is, what we're going to see is there's two different mechanisms that you find for reducing buoyancy, increasing buoyancy, reducing density. If you're more dense, you're less buoyant. If you're less dense, you're more buoyant. And there's an advantage for being buoyant in terms of maintaining your position in the water column, especially if there's not that much energy to swim around. So there's the shark, this red shark. It's got all these different things. What can you do to become more buoyant? One, you can reduce heavy matter. You can reduce the amount of muscle, that's very heavy. You can reduce the amount of skin, that's very heavy. You can reduce the amount of skeleton, that's very heavy. Inorganics, you need most of those. They're hard to get rid of. Organs, of course, you need organs. So there's some things that you can manipulate and have less of and make yourself more buoyant. The other approach is to increase light matter. So if you're a female and you have big ovaries, you have a lot of eggs with oil, you know, that makes you pretty light. If you're a male, you can't increase ovaries. You don't even have ovaries. You've got testes, which tend to be more dense than seawater. The other thing that you can do, and this is what most of our focus is going to be on, not all of it, but most of it, is that you can reduce the amount of light matter. What light matter are we talking about? Lipids, for the most part. Okay, so let's look at this idea of hydrostatic lift. You're not swimming. It just represents the difference between your density and the density of water. If you're less dense, if your body is less dense than water, you're going to tend to float. If your body is more dense than water, you've got a negative buoyancy. You've got some hydrostatic lift, but not enough to lift you up to avoid sinking. Then you're going to sink. So there's a lot of words on here that you can look at. You can pause this and read those things, but it's very common for animals in the ocean to have some kind of a gas-filled float. Fish, that's what most bony fish do, and there's other things as well. The nautilus and some jellyfish have gas-filled floats. Even in plants, algae, they've got gas bladders. So that's one approach. Another approach that you see very commonly in deep water fish and sharks and invertebrates as well. In the deep sea, there's not very much energy. Yet it's advantageous to be buoyant, to keep yourself up off the bottom. And in the deep sea, what you find is there's a lot of organisms that have some kind of a low density material that they store in their body, primarily lipids. Pressure is so great in the deep sea that having a gas-filled float is not a very good idea. It doesn't work very well. So it's fine in shallow water, but when you get into deep sea, and you have all this tremendous amount of high pressure, then gas floats tend to go by the wayside, and what you find is that all these different animals, sharks and fish and squid and crustaceans that we're going to look at, the sharks, but these other animals as well, tend to store lipid. And in fact, if you look at the livers of deep sea sharks, it's got a huge lipid content, and it's not just any lipid, but it's these low density lipids. So that's going to be our focus, is looking at the liver of sharks in general to begin with, but also in terms of deep sea sharks in particular. We're going to see all these different types of lipids that are low density that increase buoyancy, and that are one of the mechanisms, strong selection pressure for increased buoyancy at depth in the deep sea. Sharks tend to be neutrally buoyant. Fish tend to be neutrally buoyant in the deep sea. Squid tend to be neutrally buoyant in the deep sea. Crustaceans tend to be neutrally buoyant in the deep sea, because if you're buoyant, you don't have to generate very much forward propulsion, which is an expensive thing energetically. Okay, so let's talk about this neutral buoyancy. What does that even mean? If you look at a shallow water shark, they tend to be heavier than water. They'll sink if they don't swim. People have the perception that if you're a shark and you don't swim, then you're going to die. You guys are very familiar with all these different species that they don't want to swim. They don't have to. They're laying on the bottom. That's their lifestyle. They'll get up off the bottom and swim. So for them, it's actually advantageous to be more dense than seawater. So it's about 5%. You know, if we get in the water with our scuba gear, we're more dense than water. We tend to sink. If you put a scuba tank on and a wetsuit, then what you're trying to do is maintain a certain buoyancy where you're not too buoyant and you're not too negatively buoyant, but you're just right. So you wear a weight belt and that weights you down, but you want to float off of the bottom so that when you're kicking your fins, then you're generating forward propulsion, but you're not expending a whole lot of energy to stay off of the bottom. You know, if you're a scuba diver, you don't want to be kicking up all the coral and breaking the coral and being too heavy so you have to swim all the time. Of course, you also don't want to be too light so that you go floating up to the surface. So it's something that you scuba divers are very familiar with. You have this optimal buoyancy by using your BC. You put just enough air in it so you're close to neutrally buoyant, maybe a little heavier than seawater that you're in, but you're not expending a whole lot of energy to move. It's the same thing with these deep sea organisms especially. So in the deep sea, there's not very much energy there. There's not very much food. you've got a maximum, you have some kind of a meal, you get energy from that meal, you don't know when your next meal is going to come. So you don't want to expend all your energy being like a mako shark swimming all over the place. You've got to maximize how far that energy goes. So if you look at all these deep sea sharks, a lot of the deep sea sharks are these squaloid sharks in the order Squaliformes, but there's some other ones as well. If you look at those deep sea sharks, they've got certain characteristics that is very common amongst those species. We'll see there's quite a bit of variability, but the typical deep sea shark has these three different characteristics. They've got a large liver, so the liver as a percentage of their body weight is very big. Some of these, it's 25 or 30% of their body weight is the liver. In humans, we've got a pretty big liver, and our liver carries out a number of different functions, but our liver is about 2 to 5% of our body weight. It's not very big compared to our body weight. So 25 or 30% is very big. And if you compare that to other vertebrates, shallow water sharks or other fish, they're more like 5%. So a quarter of their body weight, very large amount, is their liver. And if you look at what makes up the weight of this liver, it's a very large concentration of oil. It's a very oily liver. And if you look at the composition of that oil, see what kind of lipids are in that oil, these sharks tend to have several different types of lipids that are very low density. They're not triglycerides, which is a common type of lipid that you find in most animals. They're lipids that are even less dense than triglyceride. And so if you take all these factors together and look at the liver providing all this hydrostatic lift, then what you find is that deep sea sharks, just like other deep sea organisms, are close to neutrally buoyant, which means they don't really sink, they don't really float. Their density pretty much matches the density of seawater. So they can maintain their position in the water column without expending very much energy to swim. It does take energy to synthesize these different lipids, but once you've made them, then you're like a blimp as opposed to a jet. Blimp, you can fly all the way across the United States in a blimp using a tiny little bit of energy. But if you think about how much fuel it would take a jet to fly across the United States, it's a huge amount of energy. So it's that blimp type approach. So what we're going to do, we're going to go through these different slides. I spent a lot of time studying myself deep sea sharks and their liver and buoyancy, their biochemical and physiological adaptations to depth. And one of the most overwhelming adaptations is this neutral buoyancy. And it's very interesting, I think, that if you look at all these different species of deep sea sharks, some of which are closely related to one another and some of them which aren't very closely related, a lot of them are small, but even in the big ones, there's this very strong selection pressure for neutral buoyancy. It's a big advantage to be neutrally buoyant and save all that energy from swimming. So it's very common to find neutral buoyancy amongst these. But when you start looking more closely and you compare species and you look at the size of the liver and the amount of oil in their liver and the lipids in their liver, and sure, there's quite a few species that do the same thing. They've solved this problem of neutral buoyancy in similar ways. But there's other ones, sometimes very closely related, sometimes not so closely related, that they don't achieve neutral buoyancy the same way. There's some big sharks that do it differently. There's males and females that are different size sharks, different species. So, you could answer the question, what are deep sea sharks like in terms of buoyancy? Then the very quick answer would be they're almost all neutrally buoyant. They're close to neutrally buoyant. That's a very easy answer. But if you start asking, well, how do they achieve that neutral buoyancy? Then, the standard answer would be they've got a big liver, and low density lipids, which is true for a lot of species. But there's a lot of exceptions, and there's a lot of other ways. This is going to be the focus of this section, that you can achieve neutral buoyancy. You can manipulate other things that are heavy matter, and you can manipulate the types of low density materials that are influencing your density, whether that's eggs or water or the type of lipid. All right, well, here's this number one thing that I mentioned, that deep sea sharks have a large liver. If you look at these deep sea sharks, here's some species that I looked at in my own research, and the yellow dots there on the right side of this figure, those are a whole bunch of deep sea sharks. And if you look at the liver as a percentage of the body weight over there on the left axis, you can see that there's a lot of these yellow dot, those species that are represented deep sea sharks. A lot of these are deep sea dogfish, deep sea squaloids. Then it's common for the body to be made up, 20% of the body to consist of their liver. 20, 25, even close to 30% in some of these species of their body weight is liver. Now that is a very big liver, especially compared to a lot of other animals. So there's a picture of a shark. Cut open that shark, its liver comes spilling out, oil gets spilled all over this table, and you can imagine the difficulty you would even have trying to stuff that liver back in the body cavity of the shark and sewing it up. That is a gigantic liver in that individual, and that's common. There's all these different species that have big livers. If you look over here, here's a whole bunch of shallow water sharks. And this is what I was saying before, but their liver might be 5% of the body weight or even smaller. Okay, well, what does this big liver, mean in terms of how dense these sharks are? If you look at the density of the body versus how big the liver is, then again, here's these yellow dots. These are deep sea sharks, deep sea squalids, and this is how dense their body is. So if you're neutrally buoyant, then you're not sinking, you're not floating. If you're a typical shallow water shark, then your body is about 5% heavier than seawater. That's what this represents. Here's 5% heavier than seawater. These are all heavier than seawater. They're all more dense than seawater. So they're all going to sink unless they swim. If you're right around here, a little above and a little below, then you're pretty close to neutral buoyancy. And look at the sizes of these livers, 15, 20, 25, big giant livers. Look at the sizes of these, 5% or so, means they're about 5% heavier than seawater. So deep sea sharks have a big liver, and that big liver is related to having a low density or being buoyant. The second point that I made was that these deep sea sharks have a lot of oil in their liver. If you weighed their liver and quantified how much of that liver weight was made up of oil, this is what you find. Look at these high percentages. 60, 70, 80 some percent is pretty common. 80% of their liver is oil. Now that's a lot of oil in their liver. If you look at a shallow water shark over there on the right in this figure, you see the sandbar shark. That's more typical. Shallow water sharks, maybe 20% of their liver is oil. And a lot of that is phospholipids, which are part of their cell membranes. It doesn't have anything to do with buoyancy, or little to do with buoyancy. So if you've got a liver that's 80% oil, now that oil is less dense than water, that is a lot of oil that's contributing towards making you buoyant. The third thing was that there's different lipid classes. These sharks have different types of lipids that are unusual compared to most animals. Look at most animals and you quantify the types of lipids they have. They've got free fatty acids, they've got triglyceride, they've got phospholipids. Those are very common because every cell membrane has phospholipids. All these different lipids have fatty acids, and triglyceride is the storage form of lipids in most animals. So those are very common. If you look in sharks, deep sea sharks, then there's not so much triglyceride. This is what triglyceride looks like. It's got a glycerol molecule and it's got 3 fatty acids. That's what makes it a triglyceride. Tri, 3 fatty acids, and a glycerol molecule. And so that's how we store energy. You can break this down very quickly and have it go into the Krebs cycle and generate ATP. This is a common lipid in deep water sharks. Diacylglycerol ether. So it's got this glycerol backbone, just like triglyceride, and it's got 2 fatty acids, but this third one is an ether. This third carbon has an ether chain rather than a fatty acid chain. Now, it may not seem like that different. It's also something that can be used for energy if need be. You can break that down and have those carbons go into the Krebs cycle for energy. But just this difference in the composition of this ether chain as opposed to a third fatty acid, then the density of diacylglycerol ether is about 0.89 compared to 0.92. Now that may seem like a very small difference, but 1 gram of diacylglycerol ether provides a lot more lift than 1 gram of triglyceride. So if you're storing lipid and you make this conversion, if you have the enzymes and the metabolic pathways to convert triglyceride to diacylglycerol ether, and you store that lipid, it provides a huge amount of lift compared to what you would get from the same amount of triglyceride. And then there's this third type of lipid, squalene. That's a hydrocarbon. All it has in it is hydrogens and carbons and oxygens. So it's a chain of a whole bunch of carbons, 50 or so carbons, all joined together with hydrogens and oxygens coming off of it. It's just a long chain of carbons as opposed to a glycerol and these different things. So that's what squalene looks like. And look at the density of squalene, 0.86. So again, if you're converting a lipid into squalene and storing squalene as a lipid store rather than triglyceride, and the difference in 1 gram of squalene is a huge amount of lift at a density of 0.86 compared to triglyceride. Even though triglyceride is less dense than water, it's 0.92 compared to 0.86. Now, these squalene pills have been used. People take these squalene pills because they think that it's going to fight cancer or has some other properties, and people use these low density lipids in industry because they resist high pressure and high temperature or low temperature, either one, and they're easily absorbed across the skin, so they're used a lot in cosmetics as well. But of course, the sharks, that's what humans are using them. The sharks are using these for buoyancy. All right. Well, I said that these deep water sharks tend to have those lipids. Well, if we look at those lipids, this is what you find. Here's a number of different species. The 6 gill is not a typical deep water shark, but it's still got a pretty large amount of lipid. But these ones here in the yellow, these are these typical closely related deep water sharks. The spiny dogfish is a shallow water shark. And then you've got these cat sharks, Aprosteris, APR, and then you've got the typical shallow water shark. So let's start with that shallow water shark. Sandbar shark. Look what kind of lipids. It's got a whole bunch of triglyceride and it's got some fatty acids, and it would also have little phospholipids. These would all have phospholipids. If you look at these typical deep water sharks, this yellow represents squalene, SQ, over here. 80%, 70, 60% of that lipid in their liver is squalene with a density of 0.86. That is very, very buoyant oil. Here's the other low density lipid, diacylglycerol ether, which is another 20, 30, sometimes 90% of their liver oil is diacylglycerol ether. So if you combine squalene, the yellow and the magenta, and look at that, that's 90% of their oil, or 80 some percent, almost 100% in some of these species, is one of these two oils. It's a very large percent of the oil that they have in their livers it's not triglyceride like these over here, but it's these low density lipids. And so the result is, if you look at how buoyant their liver oil is, this is what you find. This is how dense their liver oil is. So here's that sandbar shark. It's got all this triglyceride, not surprisingly. The density of its liver oil is about 0.92, maybe a little more, because it's got some other lipids. And then here's these other sharks. You get down here to these yellow ones, which again are the deep sea squaloid sharks with all that squalene and all that diacylglycerol ether. Then this is the density of their liver oil. It's 0.88. It's a mixture of different lipids, but a lot of diacylglycerol ether and a lot of squalene, so it's somewhere in between. Now this is very buoyant oil because of the high concentration of these low density lipids. And if your liver is 80% oil, and the oil that's there is this low density, you can imagine how much lift is provided just by the oil and just by these special low density lipids compared to what you'd normally find in a regular shark or regular animal, which would be triglyceride. Well, in terms of achieving neutral buoyancy, then, if you look at how dense the liver is and you look at how dense the shark is, then there's a strong correlation between those two. The more buoyancy your liver provides, the more buoyant you are. So you go down this continuum from having a liver density that gets smaller and smaller. As your liver gets bigger, you have more oil, and maybe you start to have some of these low density lipids. These are all heavy. You know, the shark density is 4 or 5% heavier than seawater, so these are going to sink. You get down here to 0, this is neutral buoyancy, and so that's where all these yellow dots are. And in order to get down here, this is what you see, that your liver density gets down to a pretty high level. The liver density is reduced, and it's full of oil, which is buoyant. It's full of these low density lipids, which is even more buoyant. And so the liver density, this is 0, the liver density. This is neutrally buoyant. And this is heavy. So if you compare the liver density to the density of the whole body of these shallow water sharks, then yeah, their liver, if you cut out their liver and threw it in the water, it would float for the most part because they're less dense in water. This is neutral buoyancy. So all of these values to the left in the parentheses are actually negative numbers. And this is very low density, very highly buoyant liver down here. And look what it does to the density of the whole body of the shark. It brings these down to close to neutral buoyancy. So the liver size, the amount of oil in the liver, and the concentration of those low density lipids all influence the liver to where these sharks are neutrally buoyant. Their liver is very buoyant and their sharks are neutrally buoyant. As I said, there's a strong selection pressure, not just for sharks, but for other fish. Look at other fish. They've got oily swim bladders. Some of them, they've got oil in their bones. They've got oil underneath their skin. They've got different kinds of, they don't have diacylglycerol ether and squalene, but they have wax ester and some other low density lipids. If you look in crustaceans, look in some squid, they have low density lipids. So it's a common thing to achieve neutral buoyancy through the use of these lipids. And looking at what I've shown you so far, you might think, well, okay, that's the stuff. If somebody asked me something, I'd say, okay, sharks have a big liver, especially deep sea sharks. Big liver, a lot of oil, low density lipids in that oil. However, that's not the end of the story. If you start looking at different species, if you start looking at males versus females, if you start looking at different sizes within the species, then it's not such an easy answer to say big liver, a lot of oil, and low density lipids, because there's a variety within these different groups. So that's what we're going to focus on now. We've seen that the prototypical pattern that you see is that deep sea sharks have a big liver. That liver has a lot of oil, and that oil has a lot of low density lipids. And so the result is you've got a neutrally buoyant shark. Well, as I said, if you start looking at the different species, they may be neutrally buoyant, but they're not all achieving neutral buoyancy through that formula up above with the big liver and a lot of oil and low density lipids. There's different patterns that different species exhibit. If you start comparing the sizes of these sharks, then you start to see differences in how they achieve neutral buoyancy. And if you compare males and females that are mature, especially, then you start to see differences between how they achieve neutral buoyancy. So the end result for most of these species might be neutral buoyancy, but the pathway that they take towards that neutral buoyancy is different. That's what we're going to focus our attention on now. So if you compare species, you've got a couple of different exceptions. You've got all these sharks over there that in the yellow that have a lot of squalene, a lot of diacylglycerate. They've got a big liver, a lot of oil, and low density lipids. These. But let's look at two of these. Here's the 6-gill, which is not very closely related to these other. It's in a different order. And then you've got this one, the plunket shark, which is, if you looked at it visually, you'd have a hard time telling it from these other species. They're small and they're dark and they live in the same place, and they're pretty closely related to these other species. Well, the plunket shark, first of all, look at the liver oil in the plunket shark. There's just a little bit of trace of squalene, the yellow. All the rest of it is this magenta colored. 90% of their liver oil is diacylglycerol ether. So you might have two species there that are dark and small, and you think, well, I can't tell the difference between this plunket shark and this other shark. But if you looked at the liver oil and you analyzed the composition of liver oil, there'd be no doubt which one was which, because one of them would have a bunch of squalene, the other one the plunket shark would have hardly any squalene. Now that's pretty different. And if you look at the 6-gill shark, this is not so surprising because they're not that closely related to the squaloid sharks. But the 6-gill sharks, it's a similar story. A lot of diacylglycerol ether and hardly any squalene, just tiny little traces of squalene. So if you look at their liver oil itself is more dense. They don't have as much squalene, so the density is closer to 0.9 than down here where you've got squalene and diacylglycerol ether. Here's these two. They're deep sea, they're buoyant, they're neutrally buoyant. However, they don't have the same low density lipids as the prototypical deep water shark. So what do they do to obtain neutral buoyancy? Well, for the plunket shark, one of the differences between this shark and the other ones is they've got a huge liver. They've got the biggest liver out of everybody. So they may not have the lowest density lipids by not having squalene, but they've got a huge liver, 25% of their body weight as opposed to 20% or even smaller percentages is their liver. It's got a huge liver, which obviously makes up for not having squalene. Got this big liver, contributes to neutral buoyancy, and you're neutrally buoyant without having very much squalene, if any. For the 6-gill shark, you've got, well, let's look at the plunket shark. Here's this giant liver. This is the amount of oil in the liver. That's the second thing. I forgot to mention that. If you look at the amount of oil in the liver, then yeah, there's a lot of oil in the liver of these different species. But this is the second highest amount of oil. So they've got a big liver compared to other sharks. They've got a lot of oil compared to other sharks. That makes up for the difference of not having squalene in your liver oil. And in the end, you're neutrally buoyant. Well, let's look at the 6-gill shark. The 6-gill shark is a different story. They don't have that big of a liver. And in their liver, they don't have these low-density lipids other than diacylglycerol ether. They don't have squalene. And so here's the 6-gill liver in terms of percentage of oil. It's right next to the plunket shark in this very large percentage of oil. So that's going to help offset this lack of squalene to a certain degree. But here's the other thing. This is what makes 6-gill sharks and sleeper sharks, another big deep water shark. But the sleeper shark is closely related to these dogfish, these deep water dogfish. But in both of these species, these big sharks, there's a limit to how big your liver can be and how much oil you can have in your liver and what kind of a size of a liver you can fit into your body cavity. So they do have a big liver. Well, they don't necessarily have a big liver, but they've got a lot of oil in their liver. That's a constraint. That is only going to provide them with a certain amount of buoyancy. But what you find in these big sharks that's unusual is their muscle. Their muscle contains about 20% of lipid. That is very unusual. If you look at all these other deep sea sharks, if you look at a typical shallow water shark, you look at a lot of animals, if you look at the muscle, it's about 2% fat, 2% oil. The muscle of these big sharks, these big deep sea sharks, is about 20% oil. That's a very oily and as a consequence, very buoyant muscle. So there's a limit as to how much lift they can provide with their liver. They try with a lot of oil in their liver. They don't have that big of livers, actually, but they make up the difference with lipid, but not stored in their oil, or not stored in their liver, rather, stored in their muscle. Now that's a very different approach. In the end, they're close to neutral buoyancy. Let's look at another group of species. Now most of these are dogfish, they're squaliformes. 6-gill is off on its own as the hexanchoformes. And then there's these cat sharks, Aprosteris. These are carcharrhinoformes. They have a completely different evolutionary history from those dogfish. Now, if you look at their liver as a percentage of body weight, there's these different species. Some of them have decent sized livers, pretty big livers. Some of them not so big down here. And if you look at the amount of oil in their liver, then this one species has the highest concentration of oil out of anybody. Some of them not so impressive. So with the size of the liver, that could make some contribution. With the amount of oil in the liver, maybe for this one species, but not for these others. There's nothing special. So some of them have pretty small livers. Some of them have livers that don't have that much oil. And if you look at the composition of the oil in their liver, then they don't have very much squalene or diacylglycerol ether. Here's these Aprosteris sharks. Yellow is squalene, magenta is diacylglycerol ether. Look at these. This has some squalene and a little diacylglycerol ether. This is a little glycerol ether. Diacylglycerol ether. This one doesn't have any. It's almost all triglyceride. They're a lot more like shallow water sharks than all of these that have this huge amount of low density lipid. Some of them have a decent sized liver. Some of them have a decent amount of liver in their oil in their liver. So if you look at the density of their liver oil, then this isn't that surprising. Here's all these deep water squaloids that have a lot of squalene and diacylglycerol ether. So here are these out here. This density is getting up to nothing special, close to 0.9, which is a lot more dense in terms of the liver, or in other words, it's a lot less contribution towards neutral buoyancy in their liver. So if you looked at these species, people have a hard time telling them apart. They look very similar externally. But if you looked at the lipid composition, it would be easy to tell which species was which. You've got this one species that has squalene. You've got this other species that's got a little diacylglycerol ether, but no squalene. And you've got this other species that doesn't have either low density lipid. So biochemically, they're very different from one another, morphologically, and their outward appearance. You know, they look a little different here, but if you had these three on a table next to each other, they would actually be pretty hard to tell apart. Biochemically, easy to tell apart. So, well, let's look at these cat sharks. It doesn't seem like they would be neutrally buoyant, does it? Well, if you look at where they're falling out, maybe they're a little more dense than neutral buoyancy, but they're certainly close to neutral buoyancy, these cat sharks. They're all in these 5 species of cat sharks. They may not have that big of a liver. They may not have that much oil in the liver. They certainly don't have these low density lipids in large quantities, and yet they're neutrally buoyant. How do they do that? Well, let's look. The answer is in the water, in their muscle. We saw it with those big deep water sharks. They're storing a lot of lipid in their liver. These aren't storing so much lipid in their muscle, not in their liver. These are storing a lot of water in their muscle. In fact, they're very watery. Now, water isn't particularly low density. Water is going to be the same density as the seawater in which these sharks are found. However, water is a lot less dense than muscle. Water is going to add to their density a lot less than muscle would. Now, it's important to have muscle to move. It's important to have muscle to be a certain size. The bigger you are, the less predators there are that can eat you, attack you. So there's an advantage for being a certain size, but there's a big disadvantage for the amount of energy that it takes to deposit muscle, the amount of energy that it takes to maintain that muscle. And in this case, there's a disadvantage for having muscle because it's more dense than water and it adds to you being heavy. So if you can reduce the amount of muscle in your body, not by being a little tiny, but by replacing that muscle with water, then you can increase your buoyancy. Not by adding a bunch of low density lipids necessarily, but by reducing the amount of heavy matter. And so the point is, if you look at these figures, this is water as a percentage of the muscle. You see all of these species out here, except for this one, have a relatively high muscle concentration of water. Here's these shallow water sharks, typical organisms, in fact, have about 75% water, some of them a little less. And you get into these deep sea sharks in general, and they tend to have more water. But look at these cat sharks out here. They have the wateriest muscle out of anybody. So they're a certain size, and the muscle is a certain size, but they have a very high concentration of water in the muscle. They're flabby, and where that slide is way down here. This is what we're talking about. Look at this. Look how watery this muscle is. And then if you took the liver out of their body, so the liver is not contributing to buoyancy at all. And you saw how dense their bodies were, their liverless bodies were. And look, none of them are neutrally buoyant without their liver. They're 4 or 5% heavier than seawater. Here's these deep water sharks that are pretty buoyant. You know, they're 2 or 3% heavier than water, as opposed to 4 or 5% heavier than water, like shallow water sharks. But all of these down here are cat sharks. They've got a very high percentage of water, and this water makes their liver-free bodies less dense, more buoyant. So they don't need a big liver, an oily liver, low-density lipid classes to float this body, because their body's less dense in the first place. Okay, well, it's 50 minutes. We've got a couple more things to talk about, but then we'll be done with this. And the second thing is that there's variation among sizes. If you look at the density of small sharks versus large sharks within the same species, and this is what you tend to find. This is the amount of squalene in the liver oil. So this is total length. And as you can see here, for these two different species, this is typical of some of these other species, that small sharks tend to have more squalene in their liver oil than big sharks. As you get bigger, you have less squalene. The amount of squalene declines. Now, the squalene is expensive to manufacture energetically. You can't easily start using it for energy. But you can use diacylglycerol ether for energy. So as the squalene content starts to decline in big sharks, the diacylglycerol ether content increases. So you've got a lot of low density lipid, but you're decreasing the amount of squalene and increasing the amount of diacylglycerol ether. And so in the end, you've got more lipid in the form of diacylglycerol ether that can be used for energy pretty quickly. And look what happens to liver density. As you get bigger, the liver becomes more dense. These small sharks down here have a lot of squalene in their liver. Their livers are more buoyant because they've got more squalene, which has a lot lower density than up as you're bigger and you have more diacylglycerol ether and less squalene. So what you find in sharks, if you look at the percentage of diacylglycerol ether, like I said, in bigger sharks, they've got more diacylglycerol ether. If you look at the overall density, you say, okay, well, there's this combination of liver size and liver oil and the concentration of lipids, the different classes of lipids, and it's the different classes of lipids that differ. And what you see is that everybody's close to neutrally buoyant regardless of the size. Some of these smaller sharks, at least for a short period of time, don't appear to be very buoyant, and so they may have to build up this low density lipid and have a bigger oil or a bigger liver with more oil. They're compensating for this with higher concentrations of squalene, but it's a temporary fix, and as you get bigger, less squalene, more diacylglycerol ether. There's still pretty large quantities of squalene. But you also, as you get bigger, have a bigger liver, and you have more oil in that liver. So you're using the combination of factors, the composition of lipid, how much squalene and diacylglycerol ether you have. You're using the size of the liver, and you're using the amount of oil in the liver, both of which increase as you get bigger. So big sharks are using bigger livers and more oil. Smaller sharks are using more squalene compared to the other lipid classes. In the end, everybody's neutrally buoyant. All right, well, the last thing that I want to mention was the difference between males and females. Now, these females are swimming around with ovaries, big ovaries that have a lot of oil. That's a source of buoyancy. But first of all, if you look at the difference in the amount of squalene between males and females, here's a couple of different species, females and males, females and males, females and males. And what you see in a number of these is that the males have more squalene than the females. Males have sometimes more, a combination of squalene and diacylglycerol ether. So between the sexes, males tend to derive more lift from these low density lipids. In fact, if you look at the density of the liver, males have a lower density liver than females. Or in other words, the liver of the male provides more buoyancy than the females. For this species, for that species, for this species, for that species, for this species, it's a typical thing is that the livers of males are being used more for buoyancy than females are. Well, what's the explanation for this? The explanation is what I mentioned before, that these females are swimming around. When they reach maturity, they start reproducing. They're swimming around with eggs in their body. These eggs are pretty big. Here's a little shark. This is probably about 3 feet long. And here are these eggs, these large eggs. They're almost as big as a little billiard ball, pool cue. They're almost that big. And they're filled with oil. That's a big source of lift, hydrostatic lift. Of course, only females have these eggs that are filled with oil. So, of course, females are deriving lift from these eggs. They don't need as much lift from their liver. So if we look at if you cut out the liver again and saw what the density of the body of these sharks, then look, females, their body after the liver had been removed is less dense than males. This is what you find in a number of cases. And if you look at this oil that's in the yolk, that's in these eggs, look at these lipids. There's this one species, almost all of that oil is squalene. That's a lot of low density oil. And if it's not squalene, there's some that have diacylglycerol ether. Or lipid, for that part. Doesn't matter what the lipid is. If it's low density lipid, then it's even more lift. But even if it's not low density lipid, it's still a lot of lift. So these females, basically, they're swimming around with little life jackets, buoyancy packets in their ovaries. Females have those, males don't. Males are relying more on their liver for buoyancy because they don't have ovaries, they don't have eggs, they don't have these oil-filled packets that they're swimming around with. That's why there's a difference between males and females. Once they reach maturity, of course, in immature sharks, they don't have those eggs. All right, well, let's just talk very briefly about shallow water sharks. For shallow water sharks, they are more dense than water. They have to swim to stay afloat. They have to generate hydrodynamic lift with their fins, or else they'll sink. They've got liver that's a certain size, liver with a certain amount of oil, nowhere near what's going on in deep water sharks, but they derive a certain amount of buoyancy from their liver. The more buoyant their liver is, then the less lift they have to generate with the fins, the more energy they can save. But they don't want to be neutrally buoyant. There's no strong selection pressure for neutral buoyancy in shallow water sharks. So, fins are a flat surface, a linear surface, and they increase at a slower rate than volume as a shark increases in size. So what you see is their fins represent a relatively smaller surface area as a shark gets bigger. It's less lifting surface. So what happens is that those fins can provide less hydrodynamic lift as the shark gets bigger, and they have to rely a little more on hydrostatic lift. So if you compare the liver size of a shark as it gets bigger, if you look at little sharks and big sharks have a proportionately bigger liver. Their liver isn't the same size throughout the life of the shark. They get bigger. Their liver becomes a bigger and bigger percentage. It's not huge, like 20% or something, but it might increase from 3 or 4 to 5%. So they have a bigger liver as they're getting bigger, which provides more lift. And bigger sharks tend to have a higher oil concentration than shallow water or smaller sharks. So as you get bigger, you rely less on your fins and you rely more on hydrostatic lift that you derive from having a big liver and having a lot of oil in that liver. All right, there's only two more things. Then this is these shallow water sharks. So if you look at what happens, as you get bigger, this is a tiger shark, then the liver as a percentage body weight gets bigger. This is a shark that has a relatively big liver, but even in smaller sharks with smaller livers, you're going to see this increase. Their liver is proportionately bigger as the shark gets bigger. And if you look at the density of the shark as they get bigger, they become less and less dense. They're less able to lift themselves up with fins, but they're more able to lift themselves up with their large liver and their oily liver. Okay, here's the very last thing. It's the whale shark swimming along, and it's got a wide distribution. This was a species that was presented a couple of weeks ago, and so we learned all about whale sharks, and we looked at the diversity of sharks. We saw that the whale shark was quite different from all the other species that you find in the Erectolobiformes, the carpet sharks. So it's in its own family in this order, Erectolobiformes, but it's very different from all the other Erectolobiformes. And the point that I made in the earlier lectures is that this whale shark contributes a huge amount to the diversity of the Erectolobiformes. And if it wasn't for the whale shark, then one might view the Erectolobiformes as much less diverse. All right, that is lecture number 2. It's an hour long instead of 50 minutes, but that's fine.